Lesson 9G, Work Energy Principle. There are three methods that can be used to solve grade 11 work energy problems, depending on the data provided in the question itself. The first method uses the theory that work arises from applying a force to move an object a distance, or work equals force times distance. Remember, the force applied, or at least a component of it, must be in line or parallel to the object's displacement. This is sometimes written as work equals force times distance with a parallel symbol between the two variables. Work is done on an object to overcome other forces, or inertia. Recall, inertia is a property of matter that resists change in an object's motion. Newton's first law is based on inertia. Larger masses have more inertia and resist change greater. For work to be done, the acting force must have some component acting in line or parallel to the displacement. In this example, 100% of the force applied is in line with displacement, which happens to be horizontal. 100% of the force applied is used to do work on the object. This model has the force applied extend off at an angle, so only a component of it is in line or parallel to the object. Less than 100% of the force applied is being used to do work on the object. This model has force applied at a greater angle away from the direction of displacement, so its inline component is very small. A small percentage of the applied force is being used to do work in moving the object. In this final example, there is no force applied in the horizontal. Not even a component of the force applied indicated is in line with motion. There is no work being done on the object by the force indicated. Method 2 uses the premise that to change an object's velocity, you need to do work on the object. Recall our example from last lesson that looked at changing the velocity of an object from 0 meters per second to 10 meters per second, and then again from 10 meters per second to 20 meters per second. In both cases, it required an input of energy to change the velocity, 2,000 joules and 6,000 joules respectively. So if work is required to change the velocity of an object, which results in a change in its kinetic energy, the change in kinetic energy of an object is the amount of work done to the object. Work equals the change in kinetic energy, which is final kinetic energy minus initial kinetic energy. If the work done by the applied force on the object is a positive, then the object will speed up. If the work done by the applied force on an object is negative, then the object will slow down. This is known as the work energy theory or principle. Method 3 uses the same work energy premise as Method 2. If an object slows down, its kinetic energy decreases. Based on the conservation of energy, that means that there must be an increase in potential energy. If work equals change in kinetic energy, then work must also equal change in potential energy. Work equals final potential energy minus initial potential energy. Again, the work done by applied force on an object is positive if the object speeds up, and the work done by an applied force on an object is negative if the object slows down. Work done on an object is to overcome friction, gravity, and inertia. Let's look at an example of each one. Work against friction. How much work is done by a 35 Newton friction force on a block as it moves 10 meters? Here's an illustration of the problem. Note there may be an applied force to the right, which is doing work to move the object to the right, but this problem looks only at the friction force that opposes motion. Friction force does work against motion. The object displaces to the right, friction force works to the left. Work by friction force equals the force friction times displacement. Work by friction is negative 35 times 10. Note the negative sign that shows the friction is opposing motion. Work by friction is negative 350 Newton meters, or equally negative 350 joules. The negative sign shows that the block has lost energy due to friction that could have been used to accelerate it. Gravity example. How much work is done by an 80-kilogram man to climb a 4-meter staircase? Well, in this case, as the man climbs the stairs, his potential energy will change. Recall, change in potential energy is work if the system is closed. Please note, humans are actually not closed systems. Work equals final minus initial potential energy. Work is final potential energy minus 0. Initial potential energy is 0 since he begins at ground level. The potential energy formula is mgh. Work is 80 times 9.8 times 4. Work is 3,140 Newton meters or 3,140 joules. Inertia example. How much work is done to accelerate the object from 10 to 20 meters per second? Again, change in kinetic energy is work. So work is final kinetic energy minus initial kinetic energy. Work is half mass times final velocity squared minus half mass times initial velocity squared. Factoring half mass is half mass times final velocity squared minus initial velocity squared. Work equals half 40 times 20 squared minus 10 squared. Work is 20 times 400 minus 100. Work against inertia is 6,000 joules.